The oldest light in the universe is still carrying a message, and part of it is missing. Roughly 400,000 years after the universe began, conditions changed. Before that point, the universe was too hot and too dense for light to travel freely. Protons and electrons existed as a plasma, a charged fog that trapped radiation, absorbing and re-emitting it continuously. Light could not escape. The entire observable universe was effectively opaque. Then the plasma cooled enough for electrons to bind with protons. Neutral hydrogen formed. The fog cleared. For the first time, photons could travel without being immediately absorbed. They streamed outward in every direction, carrying with them an exact thermal imprint of conditions at that precise moment. That release of radiation is what we now call the cosmic microwave background. What followed was simple physics. As the universe expanded, that radiation stretched. Wavelengths lengthened. Energy dropped. The temperature of the CMB has been falling ever since, in direct proportion to how much the universe has grown. Today, it registers at approximately 2.725 Kelvin, just barely above absolute zero. Every measurement taken confirms the cooling is ongoing, steady, and consistent with a universe that has been expanding for nearly 14 billion years. The CMB should be a complete record. Every fluctuation in temperature across the sky corresponds to a density variation in the early plasma, a physical imprint of conditions that existed before any galaxy formed. The map it produces should be a full accounting of what the early universe looked like at the moment of last scattering. But the record is not complete. Across specific angular scales, the temperature fluctuations in the CMB do not match what standard cosmological models predict they should. On the largest scales, patterns that should span the entire observable sky, the signal is weaker than expected, not absent, but suppressed. The data shows less variation at these scales than the physics of the early plasma should have produced. The suppression is not measurement noise. It has been confirmed across multiple independent instruments, including the WMAP satellite and the Planck mission. The anomaly persists across every systematic check performed. The fading afterglow of the universe is still carrying missing clues. Evidence gap mode requires precision here. What exactly is observed, what data is absent, and why that absence cannot yet be bridged. The observed signal is a temperature map of the CMB across the full sky, expressed as a power spectrum, a mathematical decomposition of temperature fluctuations by angular scale. At small angular scales, the spectrum matches predictions with high accuracy. At large angular scales, particularly at the lowest multipole moments, the power is measurably lower than models generate. The missing data is not raw observations. Enough photons have been detected. The gap is in the physical explanation. No model currently accounts for why large-scale power is suppressed without introducing conditions in the early universe that conflict with other confirmed measurements. The data exists. The interpretation does not close. Why the gap matters begins with what the power spectrum is supposed to represent. Each point on that spectrum corresponds to a physical scale of density fluctuation in the early plasma. Large-scale fluctuations reflect processes operating across enormous distances, potentially involving conditions before or during inflation, the hypothesized period of rapid expansion in the universe's first fractions of a second. The suppression at large scales is therefore not a minor correction. It is a signal that something in the very early universe, possibly before last scattering, behaved differently than the standard model predicts. Several explanations have been proposed. None fully account for the data without generating new problems elsewhere. One class of explanation focuses on the topology of the universe. If the universe has a finite size, if space folds back on itself at some scale comparable to or smaller than the observable universe, then large-scale fluctuations would be truncated. Wavelengths that would otherwise extend across greater distances cannot fit. The power at large angular scales would be suppressed because the modes simply do not have room to develop. The observational case for a finite topology is not established. Searches for specific signatures, repeating temperature patterns across opposite sides of the sky, or matched circles in the CMB, have not produced statistically conclusive results. If the universe is finite, the scale at which it closes must be very close to the size of the observable universe itself, which places the signature at the edge of what current data can confirm or exclude. The explanation is not ruled out. It is not confirmed. A second class of explanation proposes that inflation itself is responsible. In standard inflationary models, the universe expanded so rapidly that quantum fluctuations from subatomic scales were stretched to cosmic scales, seeding all the density variations observed in the CMB. The spectrum of those fluctuations is predicted to be nearly scale invariant, roughly equal power at all scales. The observed suppression at large scales represents a deviation from that prediction. Some inflationary models can produce large-scale suppression by modifying the initial conditions. If inflation began slightly before the modes corresponding to the largest angular scales left the horizon, those modes would have had less time to develop, producing lower power. The suppression would then be a direct imprint of inflation's starting point. What prevents this explanation from closing is that it requires inflation to have started at a very specific moment, close enough to the observable horizon that the effect is visible, but not so close that it disrupts smaller-scale fluctuations that match observations well. The precision required makes the explanation difficult to distinguish from fine-tuning. It remains a viable framework, not a confirmed mechanism. A third direction involves pre-inflationary physics. The CMB's large-scale suppression may carry information about conditions that existed before inflation began, a period about which standard cosmology makes no confirmed predictions, because inflation is supposed to have erased nearly all such information. If something from that era survived, encoded in the CMB's lowest multipoles, it would represent a signal from a domain of physics currently outside any tested framework. There is no confirmed model of pre-inflationary physics. The explanation is structurally coherent, suppression as a relic of initial conditions preceding inflation, but the theoretical space it requires does not yet exist in usable form. Each of these explanations addresses part of the suppression signal. None addresses all of it, and none can be confirmed without data that current observatories cannot reach. The gap itself has a specific character. It is not a gap in temperature measurements. The CMB has been mapped with high precision. It is a gap between the physical predictions of known processes and what the map actually shows. The suppression exists at angular scales corresponding to distances larger than most structures that can be tested against other observations. There is no independent data set that covers the same physical scales in a way that could constrain the explanation further. What the gap prevents is knowing whether the suppression is caused by geometry, by the dynamics of inflation, by pre-inflationary physics, or by something not yet proposed. Without a mechanism that accounts for the suppression without contradicting other confirmed results, the CMB's large-scale signal remains an open measurement, data that cannot be fully read. The temperature of the CMB will continue to drop. The universe will keep expanding. The photons carrying the suppressed signal will keep stretching toward longer wavelengths, lower energy, greater cold. Current instrumentation cannot access what would be needed to distinguish between the explanations. The suppression at the lowest multipoles involves so few independent modes, because large-scale patterns, by definition, repeat fewer times across the sky, that statistical confidence is inherently limited. This is called cosmic variance. The universe only provides one sky to observe, and at the largest scales, the sample size cannot be increased. No future observatory can change this. The large-angle suppression of the CMB sits in a region where observation cannot be improved by building a better instrument. The limitation is structural. The afterglow has been cooling for nearly 14 billion years. Every photon that reaches a detector carries the same imprint it has carried since last scattering. The record does not change. The gap in it does not close on its own. What the suppression is encoding, whether the shape of space, the moment inflation ignited, or something from before the framework that describes inflation existed, cannot be determined from the data available. The signal is real. The source of its missing power remains outside what current physics can confirm. The universe left a record. Part of it cannot be read.